the fourth day of the online ATAL FTP on application of artificial intelligence in power system operation and control. Today, our guest our guest speaker is Professor Satyajit Das. He will continue his session from yesterday. He is a faculty in the Department of Computer Science and Engineering, IIT Palakkad. Sir, I invite you to continue your session from yesterday. Welcome, sir. Over to you, sir.
Yeah, thank you. Thank you so much for the introduction. And I will just share my screen and resume from yesterday's session. I hope you can hear me properly, everybody. And I have shared the screen, and I hope the screen is visible. Good. Okay, so yeah, so we have seen that of course, today's processors, GPUs, and sophisticated devices will be kind of able to conduct all the compute-intensive tasks which are being offered by AI algorithms. And for that, we have several matrix multiplication libraries available for these processors that we can take advantage of and do the efficient processing of these algorithms. But before that, so we talked about some matrix multiplication conversion of these kind of layers, which are being converted from the, let's say, for fully connected layer, we have converted the filter and activation computation into matrix multiplication by just combining all the values of filters and input feature maps into row by column matrices, and then we actually did the matrix multiplication. And for that, in the convolution layer also, we can do some extension on the input feature maps by Topli's extension, and then we can perform the matrix multiplication. So at the end, the goal is to convert every computation into matrix multiplication so that we can take advantage of these libraries. But while converting these computations into matrix multiplications, we have some difficulties also. So basically, if you look at the matrix multiplication which we have done for fully connected layers, where the filters and input feature maps has these kind of dimensions like m into chw and chw into n, and these numbers are very high essentially. So here we have millions of filter values and several thousands and hundred thousands of input feature map values to be computed, and these multiplications are being computed on a huge number of elements. So basically what is being done is that all these values are not stored inside the chip itself, because the size of these are in terms of megabytes, and sometimes the size of these kind of filters, total size of these filters and input feature maps, and the weights that will be calculating are in terms of megabytes, gigabytes, and all. So the thing is that if you want to have the values inside your processor from the off-chip memory, which is kind of RAM, let's say, and you want to take the values, every values from there, and do the computation, your memory bandwidth will be going high, and your energy consumption will actually exceed the power ceiling of the processors. So what is being done is that these kind of matrices are being converted into tiles, and these tiles are essentially smaller in sizes, and they are being stored inside your on-chip memory, which may be localized cache or localized on-chip scratchpad memory, and you store those tiles and do the computation on the tiles. So you don't have to go to the off-chip memory all the time to compute all these matrix values or do the matrix multiplications. So essentially, efficient tiling or efficient, let's say, segregation of these values into several tiles is being done inside your compiler, and that is being done very efficiently as well. And while doing these matrix multiplications, we want to reduce the number of multiplications as well. So this is an analogy from Gauss's multiplication method. So if you see that this multiplication is taking two complex numbers and doing this multiplication, so here we are computing AC, BD, BC, and AD by multiplication. So four multiplications are being done into computing this result, and three additions are being done. So one is for this two values addition, and here one addition, and one is for this the negation is also considered as addition. So total three addition and four multiplications are doing for this simple two complex values multiplication. But if you want to reduce the number of multiplications, what is done in Gauss's multiplication is that it is being these components are being extracted through several parts, and let's say here k1, k2, and k3 are being computed as c into a plus b, a into d minus c, and b into c plus d, and all these k2, k1, k2, and k3 is being computed is being used to compute the real and imaginary part as k1 minus k3 and k1 plus k2. So essentially at the end you will be doing three multiplications and five additions. So for this simple two value multiplication in complex numbers, you are seeing that we are already reducing the number of multiplications up to 25%, right? So this is a toy example. Of course, in real practice, some other methods are being used to essentially reduce the number of operations in matrix multiplication. So the methods are here listed as first Fourier transform is being used in several methods, and they actually are applied on direct convolution, and they are very efficient in those cases where order of number of output square and number of filter square is the complexity, and that can be varied up to a number of up to output feature map square and log of that feature map size. So basically here you are reducing the number of computations, but again, so in the first Fourier transform, another disadvantage is that you are increasing the storage requirements due to the different types of transformation, because here you will be transforming, you will be storing those complex numbers, and the storage is going to be high. And another method is Strassen. So here you have the complexity of order of n cube, and it varies up to order of n to the power 2.807. But the main problem here is sometimes we don't have the numerical stability due to some arithmetic you can say disputes, because you will be transforming those values and then optimizing the computations, round computations. So here you have some instability in terms of your number of values you will be getting. Another method is Wingard method. So in Wingard method we have the speed up of 2.25 times speed up for 3x3 filters. So basically here the main the advantage is that speed up is very high, but with a cost of very specialized processing, because you need to have very specialized filter size to actually be compatible in this method. So what compiler does, that compiler selects the transformations based on the size you are giving. So again, if you want to compute efficiently, you need to choose your batch sizes, your filter sizes accordingly, so that compiler do the transformations very efficiently. So that is the primary method or primary goal to do this kind of transformations or optimizations. So another method that are being used is reduce instruction overhead. So basically what is being done is that your goal is to perform more max per instruction. Okay, so basically with a single instruction you want to perform more and more number of MAC operations. But of course there are some disadvantages that we will talk about, but the primary goal is that here you want to increase the energy efficiency as well as the performance of throughput to reducing the instruction overhead. So in the CPUs, what is being done in all the modern CPUs, you'll see that they are compatible with SIMD and vector instructions. So specifically for the neural network instructions, these CPUs use vector neural network instructions, which are VNN NI fused multiplication and addition operations. So basically, these are vector fused multiplication and addition. So essentially, in one instruction, you can perform MAC operations as well as several MAC operations onto several numbers of data. So that way you actually reduce the number of instruction that is being counted. And in the GPUs, mostly similarly, similar to the single instruction multiple data, in GPUs they use single instruction multiple threads. So essentially what is being done is that instead of multiple data, here multiple processing elements will be actually responsible for running multiple threads. And tensor instructions are very, very popular in those kind of scenarios where you actually perform one instruction, and in this instruction you will have several threads to be executed. And also there is HMMA instruction, which is matrix multiply and accumulate for performing 64 max with tensor core. So tensor processing units from Google essentially use those kind of instructions, as well as NVIDIA's modern GPUs, which are being compatible with these tensor instructions. They perform around 64 to 128 or even 256 number of max per instruction of tensor core. So as you can see, you are increasing the number of max per instruction, but that comes with additional hardware overhead. Okay, so on the one hand, you need to take care of the hardware overhead, and on the other hand, without increasing memory bandwidth, also you need to support all these reduced precision. Because if you see, for an example, this reduced precision is kind of a hot topic in the area of AI on edge research, because this gives a very, very high compatibility or compactness of these kind of instructions to load more and more data per instruction. Because so in one instruction you need to have, or you need to you want to execute more number of matrix multiply and accumulate operations. At the same time, you need much more data to be fed to, right? So you have the bandwidth bottleneck at the same time. So these kind of hardware bottleneck need to be countered through this kind of reduced precision. So what happens is that, for an example, if your processor is kind of getting 512 bits per cycle, that means you can perform 16 32-bit multiply and accumulate operations. And if you reduce the precisions of these bit values, you can perform 64 8-bit max. So if you reduce your data from 32 to 8 bits, that means you are actually scaling up the number of max operations for the same data or bits you are encountering. This reduced precision we will talk about more, and in modern day computation on the AI on edge, it is highly acceptable nowadays that reduced precision is working both in the inference and also in the training phases. So that we will see in the subsequent slides. And a few design considerations to be taken into account for this kind of optimization. So if you are considering the software part, then you want to reduce the number of max through some transformations we have talked about. So through different kind of transformations, Fourier transformation or Winograd transformation, you want to reduce the number of max. And also at the same time, you want to increase the P utilization. So So the number of active Ps you want to increase more. So ideally, if you have, let's say, 1,000 number of cores, you want to activate all the number of cores, or 100% utilization you want to get from the P, and software will ensure, or compiler will ensure, by balancing all the loads throughout the Ps, that you are increasing the P utilization. And this is done in the software through reducing the data to and fro through the memory. So mostly data reuse is preferred for compiler side, and that we will see how we can reuse the data and perform more number of max on the same schedule. Okay, and that is very interesting topic from the compiler side. And from the hardware side, you want to reduce time per max. So essentially, you want to increase the speed of Ps to reduce the critical path. But again, that will come with an extra hardware overhead that we'll talk about. And also, you want to increase the max per instruction through different kind of SIMD and tensor core instructions. But again, that will also require some additional hardware. So you need to see this by introducing this kind of flexibility, whether you are exceeding your additional hardware overhead, the cost you are exceeding. If you are exceeding, then you need to think or reiterate the whole process. Otherwise, you are fine with this. So there are sophisticated tools or automated tools to do all kind of optimizations that we'll talk about at the end of this session. And for increasing the number of parallel max, you want to increase the number of Ps, but that will essentially impact your area cost. It means the transistor cost you are spending. And again, you want to have support for reduced precision inside the Ps. That also you will talk about. So in the area of reduced precision, our group had a large number of works available in website. So we will talk about that also. And supporting reduced number of precisions also will come with some hardware costs, but again, you have some flexibility to get more number of max at the same time. And at the end, you want to increase the P utilization in hardware also. So from the software, you want to enact the data reuse to increase the P utilization. But for the increase of P utilization in the hardware, you want to increase the on-chip storage, because that way you will have more number of elements or more number of let's say weights or activations that you can store on chip, and that way your P utilization will go high. But that again will come with some area cost, and you want to support some external memory bandwidth for offloading or downloading all the data from the off-chip memory to on-chip memory. That is also encountering the system cost at the end. And all these design considerations you need to take into account to essentially do efficient computation in the edge, because you have always the constraints nagging into your head, because you have less area, you have less power saving, you have less you want to achieve higher energy efficiency. So that's why all the parameters you need to take into account for the implementation. So that is why this kind of specialized hardwares are making the way of AI on edge area, because the traditional GPUs and CPUs are kind of bounded in some way of flexibility. So you cannot have all the design considerations that we talked about available onto traditional CPUs and GPUs. And that is why more and more people are tending to specialized hardware for this kind of applications. And we'll talk about that. But before that, what are the priorities that we can leverage on? That are mostly the parallelism. Of course, we have multiple number of max that we can do parallelly here. So you have a huge parallelism at your disposal. That means you can achieve very high throughput to all the parallelism, all you need. And again, you need to increase the parallelism, but at the same time, you have the memory access button. So for simple example, we'll give some through an example here. So here you have one MAC unit. So this is just simply doing multiply and accumulation. So this is the P essentially at the end that we are talking about, processing element. So inside the ALU, you have this multiply and accumulate. Multiply is taking two inputs, and the accumulate is taking the output of the multiply and one input from the memory. So essentially, three memory inputs you need to complete one MAC operation, and at the end, the output will be stored also inside the memory. That is the updated partial sum. So four memory operations you need to take into account for one MAC operation. So essentially you have 1:4 ratio in terms of computation and memory operation, right? So the memory operations are huge in number. So if you parallelize these MACs, that means you have multiple number of MACs, and at the same time you are scaling off the memory operations in a huge number in exponential manner essentially. So for an example, for AlexNet, you have 724 millions of MAC operations inside the whole algorithm to be computed, and for that you need to have around 3 billion of DRAM access. So if you are accessing all the elements, for this 700 million of MACs from the off-chip memory, then you are doing 3 billion of memory accesses. So you can imagine how much energy you will be taking for a single algorithm computation for in terms of MAC operations. So this is the worst case essentially. You will not do all the accesses from the off-chip memory. So that is the target essentially to achieve. But in typical scenario, that is the case, and this is the worst case scenario as well, right? So in the input, you want to use the data, right? So basically, you want to use the data so that you go place to the object memory. So whatever data you have already loaded, you do the reuse of this data as much as you can, and up to 500 times of memory operations you can actually listen to this kind of data reuse in Alex. So this data reuse is very important in terms of flexible hardware. So you cannot do that in CPU. You cannot do that in GPU because they have already some defined structure, defined ISA, defined compiler. So you cannot do data reuse as much as possible. Of course, new libraries will add some data reuse to taken into account, but for specialized hardware, you can exploit as much as data reuse as you want. So that's why these specialized hardwares are much more important from the sense of efficient computation. So here what is happening is that different kind of reuse can be applicable. So one is convolutional reuse. So in the convolutional reuse, what happens is in the convolution layer, what happens typically the filter is convoluting through the input feature map. That means in several computations, your activations or weights are being reused, right? So you target to reuse these activations and weights for several multiplications. Okay. So for convolution layers, this is applicable. For another kind of fully connected layers, you apply many filters onto the same activation. So that means your activations are being used to multiply with or calculate partial sums with many filters, right? So here what you are doing is that you can reuse the activations. So for fully connected layers or convolutions with multi-dimensional convolution, you can actually reuse the activations. Another scenario is that you can reuse the filters as well. So essentially what happens for the batch processing, you are applying the same filter onto several input feature maps. So that means the weights in the filters which are applied to compute the partial sum in the output feature map, which are being applied into several batches of input feature maps, that you can reuse these weights, and that also can be applied for different batches in convolution and fully connected layers. So as you can see, there are several aspects of reusing data, right? So you can reuse activations, you can reuse weights, you can reuse activations, also only activations and only weights also. So that depends on what kind of layers you are approaching, and what kind of method or batch processing you are doing. So if you are not doing batch processing, so that filter reuse is not that much important. But activations and weights you can actually take into account. You can take into account into the convolution layer and fully connected layer. And there are two paradigms of this kind of parallel compute. So we are talking about parallel doing parallel compute of P's. That means you want to have multiple P's to do multiple max in parallel. But there are two paradigms for that. One is the temporal architecture, and another is spatial architecture. So here, the temporal architecture is essentially most of the traditional CPUs and traditional GPUs adopt, because here you can see that only the ALUs are kind of share the register file. Okay, so there is a global register file which can be shared among the ALUs. So all you have multiple number of ALUs sharing data through the centralized register file, and they are being controlled by a centralized controller also. So all these ALUs are feeded data through this kind of register files. So whatever data reuse you want to do through this register file only. Okay, so you have the single register file, and through this single register file you would like to share data among all the ALUs you are having inside your processor. And of course, this register file is communicating to the memory hierarchy. That means your cache and your off-chip memory. But at the end, you want to have your data to be reused inside the register. So since the opportunity here is less, that means the data use the data reuse will be less in this kind of scenario. And another paradigm is the spatial architecture, where you have data flow processing. Here ALUs are kind of connected to each other, where they can share the data among each other, and they have the memory hierarchy to talk about. So that means all these ALUs are having these register files and controls inside there, inside each ALU. So they are not centralized controlled, and they are not sharing with a centralized register file as opposed to the temporal architecture. So spatial architecture gives the flexibility of controlling each ALU independently, and each ALU will have independent register files to reuse the data for this kind of localized ALU. Okay. So as you can see, of course, there are some advantages in terms of the options. You have more options for data reuse in the spatial architecture here. So essentially in the spatial architectures, so these are the specialized hardwares we are talking about. And mostly these hardwares are essentially containing these kind of MAC operations only for your ALU. Okay, multiply and accumulate, and these register files are essentially in size of 0.5 to 1 KB of size to hold the localized data or the data reuse elements that you want to have for each ALU. And of course, you have efficient data reuse here, distributed local storage. That means locally you have register files in each ALU, so that gives you the flexibility. And moreover, you have the inter-P communication through the point-to-point connection. So if you look into the other architecture, the temporal one, here, if your ALU, this ALU is wanting to share data with another ALU, they cannot do it directly. So essentially, they need to go through the memory. So even if the local memory also, they need to go through the memory. So, so here you don't have the flexibility of data sharing among the ALUs, but inside your spatial architecture, you have the flexibility to reuse or redistribute the data internally among the ALUs through this point-to-point connection. So that way, this gives much more flexibility of data reuse inside your spatial architecture. So that, for example, you want to map one CNN convolution inside the memory hierarchy here. So that means here these multipliers are essentially being summed up by this addition operator here, and at the end you are getting the output, right? So here, if you see from these kind of these multipliers, the data can be directly passed to the ALU, which are doing uh, this addition, right? So here you can see that this one, and this one is doing the multiplication. Then they can share the data among themselves and do the addition operation. So basically, the point-to-point connection is giving you much more flexibility in terms of the internal data reuse. So if it was not there, what would have happened? You need to store all the data output from these multipliers into the centralized register file, and again you need to load the data from the register file and do the computation and the addition. So here you have the flexibility of doing this kind of computation. But the main challenge is imposes is that how to do the mapping of this kind of convolution into that memory hierarchy. So conventional compilers do the compilation based on the architecture which are underlying, but they don't go into the micro architecture, right? So they don't know that what kind of uh, connections they have. You can have connection from this one to this one, or this one to this one, or this one to this one. So that depends what kind of architecture you are operating on, but the compiler does not know about this kind of compiler. So basically, because most of the compilers are for general purpose compilers, right? So basically, this kind of mapping of these convolutions or this kind of networks into your spatial architecture is kind of challenging, and you cannot find a straightforward way to do that. And mostly this is a research challenge nowadays. A lot of academia and industry people are doing research on that, and there are several tools also do that. And they we will talk about at the end for this kind of compilation strategies that can be applied. But at the end we have the challenge, and how we actually map this kind of networks onto these architectures through data flow essentially. So we call this data flow because you can see data is flowing throughout this network of ALUs and network of your multiply accumulate, and your data is kind of flowing here. So essentially we call it the data flow approach to map this kind of networks onto the architecture of spatial type. So again, this increases the reuse of weights and activations and partial sums. As you can see here, after the partial sum, again you can reuse inside the another area. So that way you have the flexibility. But again, I'd like to remind here that this kind of approach is not straightforward. So we are working on this kind of mapping since 5 or 6 years now, and very few companies have adopted already this kind of approach. And nowadays this kind of approach is also coming in streamline or mainstream, and you will see several open source tools are available to do that. So that also we'll talk about at the end. So how we can actually do that data flow efficiently, that is also need to be understood to handle all these tools efficiently. So first of all, what kind of data movement we are talking about? that needs to be understood. So of course, your P's are there, and there's a global buffer from which you would like to fetch the data and reuse inside your P's. Okay, and essentially the P's will have very less sized register file, right? So as we have seen that the register file inside the P's varies in size from 0.5 to 1 kilobyte. Okay, and they are not capable to hold the entire millions of weights and activations inside them. So that means you need to have a very efficient approach to actually load some of the data and reuse that, again load some of the data and reuse that, and to buffer this kind of data fetching and data reloading from the off-chip memory, you have this global buffer in the middle. And what we are doing here, if you see in terms of energy cost of these data transfers from ALU. Okay, so if your computation in ALU is 1x, okay, let's say your multiplication or addition is 1x, from register file to ALU data transfer is also 1x. So you want to store more and more data inside your register file to be at the same range of energy as computation. Okay, and if you are transferring data from P to another P to another P ALU, so that means you are assuming 2x energy. And if you are transferring data from your global buffer, then you are consuming 6x. And if you are consuming data from DRAM, then you are kind of exploding the power ceiling here. Okay, so several orders of magnitude you want to face in terms of energy cost. So that's why you want to have less number of this kind. So you as you go upwards, you want to have more number of transfers. So here you want to have least transfer. Here you want to have a bit more transfer. Here more, and here actually you want to have more number of computations as you go along. So with this, it is now the time to talk about several kind of sharing, data sharing, how you can share the data. Okay, so there are several approaches how you can efficiently share the weights, the inputs, feature maps, the activations, the gradients. So essentially, if you are talking about simple inference, then you can think of weight sharing or weight stationary. So here what is happening here is that you want to store all the weights inside your register, okay, and you want to fetch all the activations and partial sums through the global buffer. Okay, so this kind of approach, you want to stress on weights more. Okay, so you want to store the weights inside your register files, and you want to share the activations and partial sums through memory fetches. Okay, and this kind of approach is used in widely in TPU. So Google has this TPU available now commercially as well, and from NVIDIA you have NVDLA. TPU also you can buy for your edge computing, and there you will be using actually weight stationary kind of thing. So you want to store all the weights inside your processor register files. That means processing element register files, and then share the partial sums and the activations. Another approach is that output stationary, where you want to share the activations and weight, and partial sums you want to store. Okay, so essentially the output of the multiply and accumulate you want to store inside the register file, and all the other inputs you want to take from the or fetch from the buffer. Okay, and one of the such example is Moon's Thinker. So they proposed this approach in 2016 and 17 respectively. Another approach is input stationary, where you are more confined to your inputs. So your activations which are coming as input, want to store them in the register files, and partial sums and the weights you want to share. Okay, so partial sums you want to store in the global buffer, and weights you want to fetch, and you have already stored in the activations in the register file, so you don't need to think again. Okay. So that's how you want to minimize the fetching of activation. And SCNN from, again, this is from NVIDIA. This approach, you can have this kind of approach. Another approach is not to concentrate only your single input or single output or single weight. Okay, so you want to have flexibility of storing different kind of variables inside your register file. So here the approach proposed in this paper SCNN, that was using the input stationary, that also can actually be flexible to use this store stationary as well. Where 1D convolution P is for 1D convolution P, you can store the filter values, you can store the input values, and also you can store the output activation. Okay, so essentially what you are doing here, you are concentrating on all the data that you are using in the max. Okay, so this kind of approach essentially averages kind of all the approaches we talked about before. And here this paper actually kind of got much more energy advantage compared to the TPU and the NVDLA that we have talked about. Well, so next is the hardware software co-design. So we have talked about several design approaches how to reuse the data inside your architecture. But if you are talking about the whole design, then you need to consider the hardware and software co-design, because at the one hand you will be increasing something, and to cope up with that increase, you need to have the flexibility to let's say, in the software side you are increasing, in the hardware side you are coping with the increase. So both of the balanced approach you need to take into account. So co-design of algorithms and the hardware, so better give you the better achievement in terms of energy and your flexibility. And also, co-design approach will be loosely grouped into two categories: so reduced size and reduced number of operations. So we have talked about this both by reduction of precision and efficiently manage the network architecture, so that you store less number of data. Okay. So we will talk about more about the reduced precision, because this is kind of hot topic nowadays. And sparsity and network architecture is more on the algorithm side that we skip for today's tutorial. And we have hardware support to increase the latency and energy efficiency at the end. And you need to ensure through the co-design that you are not exceeding the ceiling that you have already started with. And as I mentioned, that several tools are there we'll talk about. And unlike the previous approaches, this kind of hardware software co-design will give you the trade-off between the accuracy. Because let's say you are talking about reduced precision, you will see if you reduce the precision of the data, that means you are reducing the accuracy. And at the same time, if you are increasing the sparsity, you are increasing the accuracy as well. So both the hardware and software approach will give you the exact accuracy at the end, but that you need to explore as well. So it is not like you can take the black box and do the computation blindly, and at the end you will get the achievable or desired energy efficiency you want to have. So you want to do some design space exploration to reach at the point where you want to achieve. So we'll talk about the reduced precision approach first. So basically, this is nothing but reduce the bit width. Okay. And why we are reducing the bit width? This is very simple, to lessen the storage cost essentially. Okay, so we have the inputs and outputs of the MAC operations, and you want to reduce the number of data movement, and you want to reduce the storage area. So smaller memory will give you lower energy. So that is why you want to reduce the precision and reduce cost of the MAC as well. So if you look at the multiplier, if you are doing a 4 cross 4 multiply in space of 8 cross 8, you will reduce the energy by quadratically, and linearly will reduce the delay as well. So essentially what you are doing here, you are reducing the precision, you are reducing the cost of the multiply and accumulate the key operation of the whole network, and as well as you are reducing the storage amount, which will give you the lower energy, and the data movement as well. So at the same time of two data, you can two 8-bit data, you can actually move four-bit data. Okay, so that is how you want to have this energy gain into several stages of optimization. But note that bit width of multiplication and MAC accumulation are different, because at the end of multiplication you will have inflated result which you want to apply in the accumulation. So you need to have this balance of this reduction, so that you can achieve the targeted energy at the end. So basically multiplication and accumulation will be using several bit width. So that is the gist of the slide. And the impact of the reduced precision we are presenting here. So how it's on in 2014 paper, this relation between the energy cost and the area was he presented, but that essentially presents the reduced precision's energy. So if you see that this one we have already seen in previous slide, that for different precision, for your different multiply and add operations, you have different energy cost, and as well as you have relative area cost also. Okay, so essentially you will be decreasing your area if you go upwards. That means reduce precision, you can reduce quadratically, and as well as the energy also. So that is why we are targeting this kind of regime of 8-bit addition, 16-bit addition, or 8-bit multiplication as well. Okay, so for 8-bit multiplication, if you see, so this kind of multiplication determines what the bit width essentially at the end. But what are the bit widths impact on into different values? So if you see that the construction of the data, there are sign bits, there are exponent bits, and there are mantissa bits, right? So these mantissa bits are referring to the number of unique values. Okay, so if you have 23 bits in multiply in mantissa, that means you can have 2 to the power m unique values. So number of unique values are being presented with the mantissa bits. And with exponent bits, you can define the range. Okay, so if you have e bits, the range is defined by 2 to the power e. Okay, so the if you want to cover a wide range of data, then you want to have multiple bits inside your e bits e section, and at the end, sign bits essentially give you the data to be assigned or unsigned. So the total length of the data is considered as s plus e plus m, the total bit size. So if you are dealing with floating point, that means you want to have allow your data to be ranging into e bits, right? So at the same time of mantissa bit, you want to support some range also. Okay, so with unique values, you want to support some range, and here you want to have these e bits. If you are targeting fixed point or integers, then you don't need the range. So for the fixed range, that means no range, you can have the total number of the total range of mantissa you can cover. So you just exclude the e bits or exponent bits, and mostly floating points are being used in CPUs and GPUs, the 32-bit floating point values. And if you look into the reduced precision, so if you reduce the mantissa bits and if you reduce the exponent bits, you can have reduced floating point of AP16 is there. So where you are actually considering this range. For AP32, where you have E as 8, you are considering this range. So depending on the E values, you can vary the range, and depending on the M values, you can vary the different unique values you can have. So in the weights, you want to have this different number of values, right? And for accuracy reason, okay, so if you are considering the full range, if you are considering multiply, or let's say for wide range of unique values, that means your accuracy will go up intuitively. So this is very simple to understand, but you need to have the hardware support to fetch or feed all the data inside your memory. So you want to have reduced precision, but for the reduced precision, what are the concentrating data types? The concentrating data types are weights for inference, activations as well as partial sums. So for the inference, when you are doing inferences, you want to reduce the precision of weights, activations, and partial sums. And for while you are doing the training, you would like to reduce the precision of the weights, activations, partial sums, gradients, and as well as the weight averages. Mostly the gradients are being considered as the defining factor as how much accuracy you will get in the training. So gradients are most important for training, and for the inferences, all the throughout the spectrum, you can reduce the precision. Okay. So required precision can vary across the different data types, as I've said also. So not only you can have fixed range of reduced precision, you can have different precision for different data types as well. So weights, you can have a different reduction, for the activations, different reduction. So as you can see, for simple inference itself, you have, let's say, three targeting data types, and several types of reduction that you can do. So mixed precision, if you want to achieve, you want to do some exploration that what kind of reduction in which data type will give you the best results in terms of accuracy and in terms of energy. So what determines the bit width? Of course, the M bits. Okay, so because the number of unique values you want to have, that determines the M bits. So essentially, at the end, if you want to quantize your weights, let's say I'm targeting weights, and if you want to have quantization on weights, you want to decrease the M bits. Okay, and for the weights, they are not so if you are doing some uniform quantization, that means all these lines are equally distant or equidistant from each other, and you want to cover all the boundaries through this uniform quantization. So that means you want to reduce the bits uniformly, and this equally spaced will give you the weight distribution as equal length. Okay, but the distribution of weight values are not essentially equidistant. Okay, so what is being done is that non-uniform quantization. So we quantize those lengths in log table. So you go towards so mostly in the power of 2 it is being done, because multiplies with power of 2 is being done with simple shift operations. Okay, so with log quantization, you can have this ununiform or non-uniform distribution of the weights, and that suits our quantization. So for weights, if you are targeting to reduce the number of unique values, you can go with the non-uniform quantization. And fewer unique values, of course, can make transformations and composition more effective because you can group them. Okay, so reduced instruction will give you less number of weights. Okay, and reduced quantization will help you to combine multiple weights, and you can have much more compression in terms of weight size. So you can actually have much more weight confined to your given storage. And of course, if you want to reduce the dynamic range e bits, then it is possible. If you are doing for fixed values, okay, so then your e is 0. So fixed point arithmetic will consider this e is as 0, and you don't actually go into the business of dynamic range distribution. And these can be shared across different layers as well to group them, the values of the weights and different activations. And at the end, you need to have the proper trade-off between the numbers of allocated in the mantissa and numbers of allocated in exponent weights. Because if you see for this simple example, okay, your exponent, let's say AP16, for AP16 you have S as 1, okay, sign bit as 1 as always, and you have E and M as 5 and 10 in the first AP16 type of data. And if you are considering B float 16, then you are actually having the same bit width, but you are just reducing the mantissa bits and increasing the exponent bits. That means here you are actually covering much more range compared to the previous one. Okay, so it depends on what kind of range of weights you want to support, and that way you want to select the data type for that specific purpose. Okay, and these kind of data types actually support these modern architectures, modern TPUs, modern specialized hardwares. And commercially, you have NVIDIA's Pascal that you want to use, Google's TPU that I have already told about, and Google's TPU has several versions as well. V2, V3 was released last year, and Intel's neural network platform is also there, and it was also released last year that you want to use, and they use reduced precision for inference and training as well. Okay, so for inference they use essentially 8-bit fixed point data, and for the training purposes they use 16-bit floating point. So this is the ultimate conclusion of this discussion, that at the end of the day you want to have reduced precision for your inference and training, but depending on the accuracy you want to achieve, this kind of commercial processors, they use different kind of precisions for the inference and training. So for the inference they don't use even floating point, they use fixed point. Okay, so there are no exponent bits as well. So this is this is a very good way to achieve high energy efficiency in terms of inference and computing, inference and training. And if you look in the industry side, these are the hardwares available nowadays. Also, I think Intel's for the Intel Edge neural network Edge is also there. That is kind of dongle that you can use just for neural network processing, just by using as a pen drive. So that is also there, that I have not included here, but you can look into. And the main thing is that industry has accepted this kind of optimizations at the end, and still in academia we are still pushing this further. Okay, so if you see binary nets is having a single bit of weights. Okay, interestingly they have only black and white weights. Okay, and reduced number of bits means they have reduced the entire weight size to 1. Okay, So you have only single bit for weight storage. So as you can imagine, or even if you are going for 8 bits of fixed point, in the place of only one weight, you can store 8 weights at the same storage space. Okay, so this kind of architectures and approaches are there. Reduced number of unique weights for ternary weight nets are there, XOR nets are there, and nonlinear quantization is also, we talked about that. Lognet is there for this kind of weight values, where weight we will be concentrated into a particular range or boundary. And for training, that paper published in NeurIPS 2018 used 8-bit with stochastic rounding. So only single 8-bit was used for training. And in academia research, we have the flexibility to push it forward. Okay, so that is why you can see. But what is the end point, or where we will end up if we push towards this boundary? Okay, so let's look at this simple example of 8-bit into 8-bit multiplication, where we are doing simple 8-bit cross 8-bit multiplication. But if you want to reduce the 8-bit multiplier to 4-bit multiplier, you need to get the or switch off the rest of the things which are not used inside the hardware, right? So the transistors you don't want to use, you want to switch off them, and for let's say 8-bit into 2-bit of multiplication, you want to get this kind of area. So to get this kind of area, to reduce the precision, to support the reduced precision, so if you want to support the reduced precision, you have this hardware of 8-bit and 8-bit multiplier, and you want to support the reduced precision of 4-bit into 4-bit multiplier, you want to support the hardware to get all these transistors, right? So you will increase the hardware complexity as well. So you are not only decreasing the precision of computation or storage, you are also increasing the hardware cost. And one paper showed that this kind of reduction essentially will not give you very high performance gain as well, if you are going for, if you are supporting a wide range of reduction. Okay, so for this simple 19 precision scalable MAC design, what they have shown that if you have 95% of values at 2 into 2 and 4-bit cross 4-bit multiplier, and only 5% of values are in 8-bit multiplier, 8 into 8-bit multiplier, then also you just you gain only 1.3 times of energy and 1.6 times of throughput per area at the end. So this is not a huge gain if you see in terms of reduction in the precision of computation. So 95% are reduced precision computation, but then also to support this reduction, you need to support with the additional hardware cost, and that will also balance out the gain also. So that way you want to have that trade-off between the how much reduction you want and where, at the end how much you want to gain as such. Okay. So once you are trying to reduce the precision, you are also impacting the accuracy, right? So at the end of the day, you want to achieve higher accuracy as well. So it is not very easy to achieve. Of course, if you want to reduce very aggressively, then you can do some digit classification and all very easily, but it will be difficult task for sophisticated image classification. Okay. And of course, whether your reduction hardware cost is exceeding your benefits or not. So if you are going to scale the reduction in terms of 1-bit, 2-bit, 3-bit, 16-bit, you will have more overhead than if you are going for, let's say, 2-bit, 4-bit, 8-bit. So the power of 2 reduction is very efficient in terms of hardware as well. So those kind of optimization approaches you want to consider. And if you want to evaluate what kind of inference you are getting. performance in the inference, and what kind of performance in the training you are getting. And of course, if you are considering 32-bit float as baseline, then you are done. So currently no architecture considers this kind of 32-bit float process. So our last year's work at presented at date showed that with this precision reduction, we can achieve 18% higher energy efficiency compared to that 32-bit of IEEE 32-bit, binary 32-bit single precision floating point. So that was presented last year, and we showed that we can achieve at around 224 mops per milliwatt energy efficiency throughout different kernels of uh, machine learning and AI algorithms. So hardware in loop is another important aspect, because while you are doing all these kind of things inside optimizations inside your software, you want to consider the hardware as well to see what kind of impact it is making at the end. Okay, and to do that, there are tools that I already mentioned, and will give the references at the end. But you want to evaluate the how much impact it is getting in terms of max, in terms of weights. So mostly max and weights are considered as good proxies for latency and energy exploration in the hardware. And so if you consider number of max